Performance analysis of weighing functions for radar target detection. Abstract in high-resolution radars, for improvement of range resolution, encoded waveforms like LFM, NLFM, phase code etc., are used. For detection of targets as per range resolution of radar, it is essential to address the energy leakage during matched filtering. In this paper, target detection performance of Kaiser, Hanning, and Blackman windows for the detection of weak targets entering through the range side lobes of a strong target is evaluated. It is observed that the performance of Kaiser window is superior to that of Hanning and Blackman window. Keywords: pulse compression, bandwidth, linear frequency modulation, phase codes, nonlinear frequency modulation, range resolution. Introduction. In high-resolution radars, for improvement of range resolution, encoded waveforms like LFM, NLFM, phase code etc. are used. 1-3. On receive, using digital pulse compression technique, the targets are detected with better range resolution. As part of digital pulse compression technique, matched filtering is done, with FFT-based method. Due to the finite range side lobes of the autocorrelation function of transmitted waveform, energy leakage can happen to the nearby range bins. If the reflections are from a strong target, leakage will be more and will eclipse the detection of weak targets in proximity. For detection of targets as per range resolution of radar, it is essential to address the energy leakage during matched filtering. Various windowing techniques are used to suppress the energy leakage of matched filtering. The paper studies the effectiveness of Kaiser, Hanning, and Blackman windows for addressing the energy leakage and at same time maintaining the detection performance. 2. Pulse compression. Pulse compression is a signal processing technique designed to maximize the sensitivity and range resolution of radar systems. The sensitivity of radar depends on the energy transmitted in the radar pulses. This can be expressed in terms of the average transmitted power, that is, the peak power multiplied by the transmitter duty cycle. Although the peak transmitter power may be as high as several hundred kilowatts, since most radars transmit very short pulses, typically a couple of microseconds long, the average transmitted power may be much less than 1% of this value. Clearly, this is not an efficient use of the available transmitter power. Transmitting longer pulses improves the radar's sensitivity by increasing the average transmitted power. However, simply lengthening the radar pulse has the effect of degrading the range resolution of the radar, since the radio pulse is just spread over a larger distance. A technique is needed for increasing the average power without compromising resolution. Range resolution is the ability to detect two targets in space that are close to each other. If the transmitted pulse is wide enough to simultaneously dwell on both targets, the returned signal will appear to the radar as single target. The key to solving this problem is the realization that the range resolution of a radar does not necessarily depend on the duration of the transmitted pulse. In fact, it depends on the bandwidth of the pulse. For a simple rectangular pulse, the bandwidth is just 1/t, where t is the pulse duration. However, by manipulating the amplitude and or phase within the pulse, its bandwidth can be altered without changing its duration. In other words, the radar resolution can be changed independently of the average transmitted power. This manipulation of the transmitted pulse is known as pulse coding, or in some cases, pulse modulation. The pulse compression is a practical implementation of a matched filter system. The coded signal may be represented either as a frequency response h, or as an impulse time response h, t, of a coding filter. The coded signal is obtained by exciting the coding filter h, with a unit impulse. The received signal is fed to the matched filter, whose frequency response is the complex conjugate h*, of the coding filter. The output of the matched filter section is the compressed pulse, which is given by the inverse Fourier transform of the product of the signal spectrum h, and the matched filter response h*. The pulse compression is a practical implementation of a matched filter system. A matched filter is a correlation of transmitted waveform coefficients and received waveform signal. Correlation process is equivalent to convolution, if we flip the coefficients of transmitted pulse. Convolution in time domain is equivalent to complex multiplication in frequency domain. To implement the process, Fourier transform of transmitted and received waveform is performed followed by complex multiplication. Output of the complex multiplication is processed using inverse Fourier transform. The output of IFFT, inverse fast Fourier transform, is matched filtered output. There are three main waveform design techniques which are used in digital pulse compression. These techniques are linear/nonlinear frequency codes, binary phase codes, and polyphase codes. The pulse compression is based on the autocorrelation function since in the absence of noise, the output of the matched filter is proportional to the code autocorrelation. Given the autocorrelation function of a certain code, the main lobe width, compressed pulse width, and the side lobe levels are the two factors that need to be considered in order to evaluate the code's pulse compression characteristics. 3. Constant false alarm rate. This algorithm is to maintain the false alarm rate. Cell averaging CFAR or greatest of CFAR etc. can be used to maintain the false alarm rate. These algorithms are also used to avoid clutter, which is the unwanted targets. 4. Windowing functions. There are several different types of windowing functions that can applied in radar applications depending on the signal. To understand how a given window function affects the frequency spectrum, it is required to understand more about the frequency characteristics of windowing functions. An actual plot of a window shows that the frequency characteristic of a window is a continuous spectrum with a main lobe and several side lobes. The main lobe is centered at each frequency component of the time domain signal, and the side lobes approach zero. The height of the side lobes indicates the effect the windowing function has on frequencies around main lobes. The side lobe response of a strong sinusoidal signal can overpower the main lobe response of a nearby weak sinusoidal signal. Typically, lower side lobes reduces the leakage in the measured FFT, fast Fourier transform, output, but increases the bandwidth of the major lobe. The side lobe roll-off rate is the asymptotic decay rate of the side lobe peaks. By increasing the side lobe roll-off rate, spectral leakage can be reduced 3/9. Selecting a window function is not a simple task for radar application. Each window function has its own characteristics and suitability for different applications. To choose a window function, it is required to estimate the frequency content of the signal. If the signal contains strong interfering frequency components distant from the frequency of interest, choose a smoothing window with a high side lobe roll-off rate. If the signal contains strong interfering signals near the frequency of interest, choose a window function with a low maximum side lobe level. If the frequency of interest contains two or more signals very near to each other, spectral resolution is important. In this case, it is best to choose a smoothing window with a very narrow main lobe. If the amplitude accuracy of a single frequency component is more important than the exact location of the component in a given frequency bin, choose a window with a wide main lobe. If the signal spectrum is rather flat or broadband in frequency content, use the uniform window, or no window. In general, the Hanning window is satisfactory in 95% of cases. It has good frequency resolution and reduced spectral leakage. If you do not know the nature of the signal but you want to apply a smoothing window, start with the Hanning window 6/9. Even window function is not used, the signal is convolved with a rectangular-shaped window of uniform height, by the nature of taking a snapshot in time of the input signal and working with a discrete signal. This convolution has a sign function characteristic spectrum. For this reason, no window is often called the uniform or rectangular window because there is still a windowing effect. V. Properties of windowing functions. Kaiser window. The formula for generating Kaiser window for 1316 coefficients is given by where SS is the parameter to control the side lobe level. I0 is the zeroth order modified Bessel function of the first kind. SS equals 0 will result in a rectangular window. Fig 1, Kaiser window coefficients. The window and function samples are generated for 1000 points for analysis. Hanning window. The following formula generates Hanning window 12 samples. Fig 2, Hanning window coefficients. Blackman window. The formula for Blackman window 14 is: Blackman window was designed to give minimal leakage possible on side lobes. Fig 3, Blackman window coefficients. The Blackman window is similar to Hanning window. The resulting spectrum has a wide peak, but good side lobe compression. There are two main types of this window. The 4-term Blackman is a good general-purpose window, having side lobe rejection in the high 90s dB and a moderately wide main lobe. The 7-term Blackman window function has all the dynamic range you should ever need, but it comes with a wide main lobe. 6. Simulation and results. To evaluate the performance of windowing techniques, two targets are generated within a pulse repetition time, PRT, a target at 10 km distance and another at 13 km distance whose amplitude is 0.01 times that of first target. The specifications used for the simulation is: PRT, 1 millisecond max range equals 150 km. Pulse width T, 100 s. Beam width, 5 degrees. Chirp bandwidth B, 5 MHz. Sampling rate Fs, 10 MHz. Target 1 parameters. Range, 10 km. Velocity, 50 m/s. Target RCS, 100 square meters. Target 2 parameters. PFA equals 1 times 10 to the power of -6. No of training cells, 16. No of guard cells, 4. Range, 13 km. Velocity, 50 m/s. Target RCS, 1 square meter. Probability of detection and SNR calculation. Denote the range bin at which the single pulse SNR is unity, 0 dB, as R0, and refer to it as the reference range bin. Then, for a specific radar, the single pulse SNR at R0 is defined by the radar equation and is given by SNR, R0 equals PTG 2.2 s, 4p, 3kt0 BFL R0 4 equals 1, 4. The SNR is calculated for each range bin with the radar parameters shown above and listed below table. Table 1 shows a comparative analysis of peak levels of second target compared to peak level of first target with respect to the placement of second target over the span of range. It can be observed from the table given above that Kaiser window performs better than Hanning and Blackman windows for the detection of weak targets appearing on the side lobe portion of strong targets. 7. Conclusion. In high-resolution radars, for improvement of range resolution, encoded waveforms like LFM, NLFM, phase codes, etc. are used. For detection of small targets which are close to bigger targets as per range resolution of radar, it is essential to address the energy leakage during matched filtering. Various windowing techniques viz., Kaiser, Blackman and Hanning windows are studied for the suppression of the energy leakage of matched filtering. To evaluate the performance of windowing functions, a strong target and a weak target is considered for analysis. It was observed from the simulation that Kaiser window performs better for the detection of weaker targets emerging through the side lobe portion of strong target. Acknowledgements. The authors would like to thank Sri Umesh K.S., General Manager, NS2, Bell, for giving us the opportunity to work on this project. He provided the motivation through his vast knowledge and experience in Bell radars. It is our duty to thank SMT Dharni B., AGM, NS2, Bell, for her valuable suggestions and support during the course of the project. It was a good learning experience for us to work with their vast experience in radar signal processing areas.